Okay, so do you have any questions on anything? Homework, material? No? You could do all the homework problems? Great. The last one? Which was the last one?
It was like the rectangle with 5 circles.
What number is it? What number?
74.
74, okay. Okay, so in problem 74, I think you have to have think of it maybe like a fluid problem. Think of those little circles as being faucets or maybe pipes that are open with certain probability or closed with a certain probability. And all you need is one path from the left side to the right side. Does that help? No? Okay. So this is problem 74, I guess you all realize. Okay, each unit fails independently with probability P. And the question is, what's the probability the following system works? So I think that means, if you think of these as being pipes or something, they all has to be an open path from this side to that side. So you pump water in here, it's going to come out there. All it needs is one opening to get through. So what's the probability that it's operational or the water can get through? This one is open with probability 1 minus p. This one's open with probability 1 minus p. This one with probability 1 minus p, etc. So you might ask, what's the probability that it fails? That would be 1 minus the probability that it works, right? How could it fail? Well, all three of these passages must be closed. So three things must happen. The top, middle, and bottom must all be closed. And they're independent, so what's the probability that, so it would be the probability that the top is closed times the probability the middle is closed times the probability the bottom is closed. And what's the reason for that? Why is this equal to that? That's
multiplication principle.
right. Well, also you might say that's independence. All these things, all the circuits here, or whatever, are independent. So this is the probability that they all fail. That'd be the intersection of this fails, this fails, this fails. And the probability of the intersection of independent events is the product of their probabilities. So what's the probability that the top is closed? Well, that'd be P squared is only one of those has to be closed.
So P plus P?
Well, how about this? Which is easier to compute? The probability the top is closed or the probability the top is open? Yeah, how could the top be open? Both things have to be open, right?
Yes.
And what's the probability the top is open? So it would be the probability the top is closed.
1 minus.
1 minus that, right? So this would be 1 minus p squared. And what's the probability the middle is closed? Well, there's only one faucet or whatever there. And that would be probability p, right? And then for the bottom to be closed, that looks like the top. So we just square that. Everybody see what I did? This is the same as this, so I just took this term and squared it. Okay. So maybe I'll write here. And maybe just to be excruciating in details, all right. What's this event? The intersection? All three of them are closed, so that's this. Okay. Independence is a statement that the probability of the intersection is the product of the probabilities. Okay, so that's what we use from here to here. Okay. It's time to talk about random variables. This is a way to quantify events that we model using probability theory. We just assign values to outcomes. So if you toss a coin, it'll come up either heads or tails, and we don't assign a number to that usually, unless you're maybe gambling. And if you win $1 every time a head comes up and lose $1 every time a tail comes up, you might think of looking at this sample space and defining a function from the sample space into the real line such that the value of having a heads is 1, and the value of this function on tails is -1. So this would represent just a simple one-time trial gambling event where you win $1 if the coin comes up heads and lose $1 if it comes up tails. Okay, this kind of function from a sample space to a real line is called a random variable. Probability isn't a real old subject. This name was chosen in the 20th century. I happened to meet the guy who was involved in naming this, coming up with the name random variable. He was having an argument with another person in probability theory. The two people were Joe Doob and William Feller. I knew him, and he told me that he thought they should be called chance variables, and he thought they should be called random variables, and they gave each other their reasons, and neither was convinced by the other one. And they decided it by tossing a coin. And Feller won. So to extend that, you might think of having a longer game. And this is a long list, maybe all sequences of length n whose components are either h or t. In other words, two symbols, h or t. We could also think of these symbols as being replaced, h being replaced by s, and t being replaced by f. And this comes into a lot of statistical problems in analyzing, say, effectiveness of medicines. You you perform experiments where you give certain medication to n patients, and you record whether the medication succeeds or fails in treating the symptoms or curing the symptoms. So a random variable here might be the number of h's that occur in the sequence, the number of heads. Or if you replace h by s and t by f, this would be the number of successes in n trials. Okay, so generally, a random variable is a function on a sample space with real values. Very simple. A random variable is a function on a sample space with real values. Okay, so there is a probability on the sample space. And we look at the probability of all outcomes for which the random variable has a value less than or equal to x. Probably should write this out. This would be the probability of the event. It's a set of outcomes omega. These are elements of the sample space, so maybe I'll write it even more detailed. It's the probability of the set of omega in capital Omega such that the value of the function or random variable at omega is less than or equal to x. So instead of writing all of this out, I'll just write capital X is less than or equal to little x. Okay. So in the two examples, maybe in the second example, this would be the probability of the set of sequences of length n such that the number of successes was less than or equal to some number little x. This is a function of little x. Okay. Probabilities are always between what two numbers? A probability is always between what two numbers? 0 and 1. So this function capital F will always be between 0 and 1. If little x is less than little y, can we say anything about the relative size of these two sets? Like if this is 9 and that's 10, look at the set where of omegas where capital X of omega is less than or equal to 9, and look at the set where it's less than or equal to 10. Which is harder, be less than 9 or less than 10? Being less than is a restriction, right? So being less than 9 is more restrictive than being less than 10. So this set is a subset of this set. All right? And now if you have one set as a subset of another, what about the probabilities of those sets? Probably this set would be smaller than that set, right? So if x is less than y, capital F of x is less than or equal to capital F of y. That means capital F is a non-decreasing function. If you agree that increasing means that you could have equality, you might also say it's an increasing function, but not necessarily strictly increasing. What do you think this limit would be? And would it exist? This number is always bigger than or equal to 0. Also, as x gets smaller and smaller, this number gets smaller and smaller by that property. So this is decreasing, and it's bounded below, so it converges to something. What do you think it converges to? Bounded below by what? 0, right? If you replace this by minus infinity, what would be the probability that a number is less than or equal to minus infinity? 0. Okay, so this limit is 0. And the limit as x goes to plus infinity. Is 1. Okay, and I guess one other property is that f is right continuous. Okay. So okay, so this is the function that captures all the statistical or probabilistic, oops, this is capital X here, sorry. Statistical information about the random variable x. And this is called the distribution function. Different random variables will have different distribution functions. And we identify random variables by their distribution functions. We'll give names to distributions. We'll say that the random variable has that name, like normal or uniform or Poisson. Okay, so let's first maybe point out that there are two major classes of random variables. Discrete and continuous. X is a discrete random variable. If its distribution function let's see, okay. I'll say it that way. It has jumps interrupted by flat spots. So it's flat, then jumps up, flat, then jumps up, flat, then jumps up. So the graph would have to look like this. It's 0, and then it jumps up. Then it's flat for a while. Then it jumps up. Then it's flat for a while. Then it jumps up. Here's the value 1, flat, and jumps up. Maybe it jumps to 1, and then can't go any higher. So if the graph looks something like that, we say it's a discrete random variable. X is a continuous random variable. If its distribution function is continuous. So here the graph of the distribution function would have to look something like this. Okay, so if the distribution function looks like this, jumps interrupted by flat spots, we call that a discrete random variable or discrete distribution function. If the distribution function of a random variable looks like this, we call the random variable continuous. So continuous or discrete refers to properties of the distribution function. Okay. So let's look at examples of discrete random variables. Oh, by the way, the book would call a distribution function a cumulative distribution function. Okay, I will often drop the word cumulative and just use distribution function. And they abbreviate this CDF. Okay, so let's first examine examples of discrete random variables. The most basic example is called the Bernoulli distribution or random variable. So we take some number between 0 and 1. And I'm not going to say anything about what the sample space is or what the probability is, except that the probability that the random variable is 0 will be 1 minus p. The probability that it's 1 is p. So think of having a value of 1 for the random variable as being a success, and 1 minus p is, 0 as being a failure. The distribution function will look like this. If little x is over here, what's the probability that my random variable is below this value? Well, what values can the random variable have? 0 or 1? And that exhausts everything because what's 1 minus p plus p? 1. So the union of x is 0 and x is 1 has probability 1. They're disjoint, right? So what's the probability that capital X is to the left of anything over here? 0. So the distribution function is 0 until I get to 0, and then it jumps. The value at 0 is 1 minus p, so I jump up to 1 minus p here. So this circle down here is empty, and then I jump to 1 minus p. That's probably x is 0. Now what if x is in here? What if little x is here now? What's probably capital X is less than or equal to that? What values does the random variable take on with positive probability? 0 and 1. Which ones are below here? Only 0. So probably capital X is less than or equal to this value is the same as the probability capital X is equal to 0. So the value of the distribution function will not change until when? Until we get to 1. And then it'll jump to 1. It'll have a jump of this size. Okay? Because think of having the little x over here now. What's the probability that the random variable capital X with this prescription is smaller than this value? Well, the probability that capital X is less than or equal to this is 1, because what are the two values it could have? 0 or 1, and they're both less than this, right? So the value of the distribution function is 1 from then on. So this is the distribution function, or CDF, cumulative distribution function for the Bernoulli random variable. Or we say Bernoulli distribution function. So if we call a random variable Bernoulli random variable, we mean that it satisfies this. So we describe the random variable in terms of its probabilistic properties, or in terms of its distribution function. Okay? The next most basic one is the binomial random variable. In this example, n independent Bernoulli trials are performed. I.e., an experiment with, everybody know what this means with? Probability P of success, 1 minus P of failure, and X is the number of successes in n trials. That's the number we assign to sequences of S's and F's, sequences of length n. So what would the outcome be of n Bernoulli trials, where you could have either a success or a failure? How would you record that? You'd record an S every time you had a success and F every time you had a failure. So you'd have the sample space would be sequences of length n, whose components are either S or F, and then X would just be the number of S's that appear in the sequence. Okay? So what possible values can X have? If we're counting successes in n trials, you might have 0, 1, 2, up to n. So X will be some number between 0 and some integer between 0 and n inclusive. What's the probability that X is equal to k, where k is a number between, an integer between 0 and n? What's the probability of k successes if you perform an experiment independently n times, and the probability of success each time is p? Well, think of having n spaces here, and we have to fill those spaces with S's and F's. How many S's? K. How many F's? N minus k. This is a problem where the probability of each outcome with, well, I guess it's not equal, but what's the probability of getting this particular sequence here? Maybe S, S, up to k, like that, and then from that point on we get F's. What's the probability of that outcome? Well, what's the probability of success the first time? P. Okay, what's the probability of S 2 times in a row? P squared. So the probability of S k times in a row would be P to the k, followed by probability of getting failures the rest of the time. It'd be 1 minus P to the n minus k, right? Okay. Now, does it matter that they occurred consecutively? What if I take this same number of S's and F's and distribute them in a different way? What would the probability of that sequence be? The same, right? So all the sequences with k S's and n minus k F's have probability P to the k, 1 minus P to the n minus k. So the probability of that event, x equal k, would just be that probability of one particular one times the number of sequences of length n that have k S's and n minus k F's. So we know that we multiply this number times the number of sequences of length n that have k S's and n minus k F's. Well, how many are there like that? How many sequences are there with k S's and n minus k F's? Well, what do you have to do? You have to pick k places for the S's. Yeah, so n choose k is the number. Good. Simply because you have to pick k positions for the S's, the rest get F's. Okay? And this is for k equal to 0, 1, up to n. A random variable that has this property is called a binomial random variable. And there are some parameters here. I'll abbreviate it: binomial with parameters n and p. N is the number of trials, p is probability of success. Very useful random variable. Okay, now in both these cases, we started out with this function, the probability that it's equal to particular values, as opposed to the CDF. This function is called the PMF, probability mass function. In this case, how can you get from the probability mass function to the distribution function? Well, from up to here it was 0, then it jumped. Had a jump size equal to the value of the PMF here. And then it has another jump here equal to the jump size here is equal to the value of the PMF at 1. Right? Here it would be the sum over y less than or equal to x, or maybe I should say k less than or equal to x, integers. Well, I'll say sum over y less than or equal to x, p of y, where p of y is the probability capital X is equal to little y. In discrete random variables, this will be a countable set at most. The set where this is different from 0. Similarly, over here, if we add up the values of this is the probability mass function. If we add up the values less than or equal to a particular value of x, let me call this P of k. Okay, so P of y is either 0 or some non-zero value, and it'll only be non-zero where x can actually occur with positive probability. Okay, so this is the relation generally between a CDF and a PMF. Okay, if you know the PMF, you can get the CDF by this summation. We could try to draw this so it's a little bit difficult. For their Bernoulli random variable, I'm sorry, binomial. The commutative distribution function will be 0 until you get to 0. Then it'll have a jump. The jump size will be p of 1. The probability that, I'm sorry, p of 0. The probability x is 0, which would be n choose 0, which is 1. P to the 0 is 1. And 1 minus p to the n. So a really small jump if n is big. Is 1 minus p. And then it's flat until you get to 1. And then it'll have a jump of size p of 1. So this jump size here is p of 0. Then you have a jump here. And it'll be flat until you get to 2. And the jump size here is p of 1. And you'll have a jump at 2. And it'll be flat until you get to 3. And the jump size at 2 is p of 2, etc. Okay. So every time you come across, in this case, the random variable has only integer values. Every time you meet an integer, you'll have a jump. And the jump size will be the value of the PMF at that integer. And then finally, when you get to n, after n, the value of the function is 1. Because there are no more jumps to be added. Okay. Okay. Example 3. Geometric random variable. And then will x be the random variable, which is the number of the trial on which the first success occurred. So it'd be something like this. You toss a coin until you get a head. If that occurred on trial number 3, in other words, if you had the sequence tail, tail, head, x of that sequence would be 3. Or you roll a die until you get a 3. If that occurred on trial number 7, then x would be 7. So in other words, if you had something like 2, 4, 5, 4, 6, 1, 3, x of that sequence would be 7. Or you have children until you get a girl. So if that occurs the first time, then the first success occurs on trial 1. Okay. I think I misspelled here. Are there any engineers here? Here's an idea for you. I'll give it to you for free. Make a blackboard that's auto-correcting. So if a professor misspells a word, it automatically puts the right one in there. Okay, so what kind of values can x have? Well, when could success occur? Might happen the first time you try something, or the second, or the third, or the fourth, or the fifth. So here x could have the values and it keeps going, right? For any value in there, what's the probability that x is equal to k? What's probably the first success occurs on the kth trial? Well, what kind of outcome do we have to have for this to be true? I'm going to record the outcomes here. What do I have to have here? Failure, 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 success. And what's the probability of this sequence? Well, these are independent trials, so I just multiply the probabilities of the individual outcomes. The probability here is 1 minus p, 1 minus p, 1 minus p, 1 minus p, p. So how many 1 minus p's do we have? K minus 1, and then a p. So it would be 1 minus p to the k minus 1 times p. And this is for k equal 1, 2, 3, etc. All right. What should this number be? The probability that x is finite? 1. So this sum better be 1. Is it 1? So I did two things from here to here. I factored out the p because the p doesn't depend on the k, and I'm summing the k, right? So this doesn't depend on k, so it's the same for every term, so I can put it out in front. And then I changed variables. I set k minus 1 equal to j. Instead of this to the k minus 1, I have it to the j. And then I have to adjust the limits of the summation. I started with k equal 1. When k is 1, j will be 0, and it'll go up to infinity. And what's this equal to? Do you remember this series? R is less than 1. This is finite.
1 over 1 minus
Yeah, and what's this series called? Geometric series. That's why we use the word geometric. Did I use the word geometric? Yes, I did. Somewhere. Yeah, over there. So this is 1 over 1 minus which is 1. Okay. And before the break, let's do one more. I think this next one's called negative binomial. Negative binomial, related to geometric. This time we'll perform independent Bernoulli trials until R successes occur. So it's something like you go to the gym and you're going to shoot free throws until you made 10 free throws. And I see people smiling because they think that would take me a long time. Or you might think of some of your favorite professional basketball players. This random variable could take on the value infinity, maybe. Or maybe not. So x would be the number of the trial in which the rth success occurs. So this is asking how many trials did I have to do before I got my rth success? So how many free throws do I have to throw until I've made 10? That's the x. And probability of success here will be p, and failure again 1 minus p. So let's try to write down the PMF for our new random variable. X could take on any value in what set now? What's the least number of trials you could perform and get R successes? I think I heard somebody say it. R, right? And it could take forever, or any arbitrarily large number. So we have to go out, include all of them. Now, what's the probability that it took k trials to get R successes? Let's try to draw a picture. One thing I know for sure, if the rth success occurred on trial k, that S goes here. Now what else do we have to have? How many other successes are there? K minus, R minus 1, yeah. So there are R minus 1 successes that have to go in here. So what would be the probability of any particular sequence that had, well, R successes and the rest failures? The probability of success is P, and these are independent trials, so we'd have a P to the R, and then 1 minus P to the and so now we just have to, all the sequences with R S's and K minus R F's have this probability, so we just have to count the number of sequences that have that many S's and F's. Okay, but this S has to go here. Why is that? Right, that's the one where we got the last success, right? So how many ways are there to put R minus 1 successes in here? It'd be choose R minus 1. Yeah. You just have to choose R minus 1 positions. I'm sorry, yeah, to put the successes from the K minus 1 positions. So that would be the PMF for the negative binomial. And then the CMF would be I'm sorry. And so this would look something like this. Here's R, R plus 1, R plus 2, etc. This CDF would be 0 until you get to R. And it has a jump of size. Well, whatever you see here with R, k equal to R, when k is R, this becomes 1 minus p to the 0. So you get p to the R. Here, this is R, so this is 1. So you get a jump of size p to the R. And it's flat, and then you get a jump of size p of R plus 1. And then you get a jump of size p of R plus 2, etc. So every integer has a small jump. And it keeps jumping like that. It never reaches 1. but it approaches 1 as you go further and further to the right. Okay. All right, we'll take a break and come back and do more. Okay, perhaps one of the most important random variables is called Poisson. So here we have lambda positive, and I'll use this to indicate that the random variable has Poisson distribution with parameter lambda. The random variable can take on any natural number value. Probably x is equal to k is lambda to the k over k factorial e minus lambda. So that's the PMF. The sum of the PMF has to always be 1. Is it true in this case that this sum is 1? Now this e, I have to sum this thing, but the e to the minus lambda doesn't depend on k, so I'll pull it out. And that term lambda to the k over k factorial is left inside. What happens when I sum that from k going from 0 to infinity? Do you recognize that? Sum k equals 0 to infinity lambda to the k over k factorial. For, yeah, that's e to the lambda. That sum is e to the lambda. So we get e to the minus lambda times e to the lambda, or 1. Okay. This random variable is used in counting, where there are large numbers of independent events, each with very small probability. Like you might consider a block of a radioactive substance, like the material in your smoke detector in your apartment. And you might ask the question, how many alpha particles will it emit in the next 10 minutes? That would be modeled by a Poisson random variable. Why is that? It's actually, this is actually an example of a binomial random variable, the count of the number of alpha particles. It's actually something more like a binomial, where each atom emits an alpha particle with some small probability, and the atoms are acting independently. So you have something like a large number of trials. How many trials would that be? How many atoms would be in a little block of radioactive substance? On the order of what? 100? 1,000? 10 to the, what's Avogadro's number? 10 to the, it's on the order of 10 to the 23. So it's like you have 10 to the 23 atoms or on that order, and they're all tossing a coin with a very small probability of success. And if the coin comes up heads, they emit an alpha particle. Do you think that probability is big or small with the thing in your smoke detector? Well, you better hope it's small. Otherwise, you'll be flooded with radiation. So let's look back for a moment to the binomial random variable. And see its relation to the Poisson. So here I'm going to take a sequence of random variables. And the probability of success will depend on n. And I'm going to assume that the limit as n goes to infinity of n times Pn is lambda. So this is the probability of success on a given trial. And here's the number of trials I'm trying. So n times the probability of success is coming out to be some number lambda, which I'll assume is in 0 to infinity. It will be positive, but it won't be infinity. Let's compute the probability that xn is 0. Well, what do we recall about binomial? In this case, it's p sub n to the k, 1 minus p sub n to the n minus k. Right, that's what we call the binomial random variable with parameters n and p sub n. Before we just had p that didn't depend on n. Now we're going to consider where it does. So the probability xn is 0 would be what we get when we put k equals 0 here. N choose 0 is 1. Then we get pn to the 0, that's 1. Here we get 1 minus pn to the n. And now what happens to that as n goes to infinity? Anything? Well, there's a delicate balance here. This number is less than 1, right? And we're raising it to a power n. If you raise a number less than 1 to a power n, it goes to 0, right? On the other hand, this number is going to 0. Pn is going to 0, right? Because n times Pn is going to a finite limit. And here we'd have 1, and 1 to the n would be 1. So this might be 1, it might be 0, or it might be something in between. How can we tell? Well, what information do we have about Pn? Only one piece of information is given. N times Pn is converging to lambda. For simplicity, why don't we just assume n times Pn is equal to lambda? The same argument will work. Let's assume n times Pn is actually equal to lambda. In other words, Pn is lambda over n. Okay? And then in here, what can we do? Well, let me say that and then this would be approximately equal to 1 minus lambda over n to the n. And what does that do as n goes to infinity? This is one of the most fundamental limits in calculus. Converges to, do you remember this one? Do you remember the name L'Hopital? I think you did this limit with L'Hopital's rule. This converges to e to the minus lambda. So if n times Pn converges to lambda and xn is binomial with parameters n and Pn, probably xn is 0 converges to e to the minus lambda. Okay. If x is Poisson, what's the probability x is equal to 0? Lambda to the 0 is 1. 0 factorial is 1. E to the minus lambda. So these have the same probability of being 0. So when n is large, probably xn is 0 is approximately the same as the probability that a Poisson random variable is 0 with parameter lambda. Let's consider now the probability that xn is k plus 1 divided by the probability that xn is k, and see if this has a limit. If so, if we can figure out what this is, Then we can figure out what probably xn is equal to k plus 1 is converging to, because we know what this is converging to. So we can put k equals 0. We know this goes to e to the minus lambda. If we can figure out what this ratio is, then we get the limit as n goes to infinity, probably xn is 1. And then we could put 1 in here and get the probability for 2. Put 2 here, get 3, etc. And the reason I did this is similar to the one last time in the coyote capture problem. Remember, we looked at ratio, fn plus 1 over fn, and got a lot of things canceling due to the fact that we have factorials. Similar thing will happen here. What does this become? Well, we'll just use that definition there. Here we have n, choose k plus 1, and then pn to the k plus 1, 1 minus pn to the n minus k minus 1. In the denominator, it's n choose k, pn to the k, 1 minus pn to the n minus k. Okay? All I did was use the definition of binomial. All right, now some simplification should occur due to the fact we have all these factorials here, and then look at this. We'll get a nice cancellation with the PNs. And this stuff, well, we'll handle that in a moment. So let's see what happens. So maybe I'll handle the factorial stuff separately. Does that look right? Oh, no, I'm sorry. I inverted. Let me do this again. Okay. Now I have it right. Well, this cancels with this. K factorial over k plus 1 factorial is 1 over k plus 1. And then what about this? Here I'd get an n minus k from this ratio. Is that right? And now we multiply that by, let's simplify this part, I guess. It becomes that. Putting the two together, I just multiply those two. I get a 1 over k plus 1. I get an n minus k times Pn. And then I get a 1 minus Pn to the minus 1. Now let's consider what happens as n goes to infinity. This doesn't move. What does this do? K is fixed, but n is going to infinity. Well, let's examine it here. What does the ratio n minus k over n do as n goes to infinity? Goes to 1. What does n times Pn do? Goes to lambda, so this converges to lambda. So the second part here converges to lambda. So I'm going to write it as lambda over k plus 1. And what about 1 minus Pn? What does that do as n goes to infinity? Pn goes to 0, so 1 minus Pn goes to 1. 1 over 1 goes to 1. So we get this ratio here. So we know this so far. Limit as n goes to infinity, Pn of k plus 1 over Pn of k is lambda over k plus 1. And the limit as n goes to infinity, Pn of 0 is e to the minus lambda. Where Pn of k is this. Right?
Should there be an e in that? Because did we
Where?
account for the 1 minus Pn for the negative?
Where? In this one?
The last part of it? The 1
Yeah.
minus, do we account for that?
Well, Pn goes to 0, so 1 minus Pn has to go to 1.
Oh,
So no e here. The e is going to come from that. So what's the limit as n goes to infinity, Pn of 1? Does it exist? What does the ratio Pn of 1 over Pn of 0 do? That's what you get when you put k equals 0 here. That goes to lambda over 1, or lambda, right? When you have 0 and 1 here, you get lambda. And Pn of 0 goes to e to the minus lambda. So this goes to lambda e to the minus lambda. What about the limit as n goes to infinity, Pn of 2? Well, I want to use the fact that I know how these ratios behave. What does this ratio do? That's when k is 1. What do we get? Lambda over, when k is 1, lambda over 2. And what's this? Lambda e to the minus lambda. So we get lambda over 2 times lambda e to the minus lambda, or lambda squared over 2. And 2 is the same as 2 factorial. What about the limit as n goes to infinity, Pn of 3? This would be what we get if we put k equal to 2 over there. And what does that give? Lambda squared, no, lambda over 3. If we put k equal 2 in the top line over there, we get lambda over 3. And then this, we know, converges to that. Lambda squared over 2 factorial e to the minus lambda. And what's this? Lambda cubed over 3 factorial e to the minus lambda. If we keep going like that, what's it going to give for general k? This. Lambda to the k over k factorial e to the minus lambda. Okay, so Bernoulli trials, large numbers of Bernoulli trials with very small probability of success. In fact, if this happens, then a Bernoulli random variable is almost like a Poisson random variable. And that's why Poisson random variables come up so much. They're used, for example, in modeling the number of people that go to a 7-Eleven. Let's say you're in Taipei. There are 7-Elevens there. The number of people go to a 7-Eleven between midnight and 1 a.m. This is a model using Poisson random variable. Why is that? Well, are there a lot of people in Taipei? Yes. What's the probability that one of them, picked at random, decides to go to 7-Eleven between midnight and 1? Is it big or is it small? It's small. And in fact, the population of Taipei times the probability the individual goes there is some number between 0 and 1 about. Well, no, it doesn't have to be a number. It's some finite number. And so the number of people, and all the people that are deciding whether or not to go to 7-Eleven are doing this independently. Somebody's in an apartment on floor 7 on a certain street. Another person's in an apartment on the ground floor on another street. Another's in a restaurant. Another's in a bar. They don't communicate with each other. Their decisions are more or less independent. So you have a bunch of independent Bernoulli trials, a lot of them. A small probability of success. Success is what the person decides to go to 7-Eleven. So the number of people that go to a 7-Eleven in a certain time span in a big city would be modeled using a Poisson random variable. It's also used in reproduction. Some plants, for example, I remember there were elm trees when I was young. They all died since then. But they would make just thousands and thousands and thousands of seeds. They were little seeds that looked like oatmeal. What do you think the probability of success of these individual seeds was? Well, there weren't elm trees everywhere. There were just a few elm trees. So the probability of success of any given seed was kind of small. So the number of offspring of a given elm tree would be modeled using a Poisson random variable. It's used in modeling the number of alpha particles emitted. It's used in many, many, many applications. So Poisson random variable has this PMF, and it comes from, generally speaking, this kind of phenomena, a large number of independent trials where the probability of success is very small. Okay, now that's a bunch of examples about discrete random variables. Let's consider some examples of continuous random variables. Any question on this? By the way, what we just did here is called the law of rare events. One of the most fundamental results in probability, along with the central limit theorem, which we'll do later. Remember, this means so as a preliminary, let me say that if capital F has a derivative, then mostly true. There are some examples where this doesn't work. Capital F would be the integral of its derivative. And little f is called the density of capital F. Or of x. Sometimes it's got the more fancy name, probability density function. And we usually identify random variables x by specifying the density. So most basic example would be okay, then the random variable satisfies this property. The probability that the random variable is smaller than a value x is integral minus infinity to x of little f of y dy. Okay, that's what it means generally. If I say that capital X has density f, little f, that means this relation holds. Now, for this particular example, what does this function look like? The density function looks like that. Here's the graph of little f. It's 1 here and 0 everywhere else. So what does this integral look like? What would it look like if I take a little x over here? It's 0, because I'm integrating 0 from minus infinity to here. If I move the little x over here, it's 0 all the way until I get to here, right? So capital F capital F looks like this. And then what happens? I'm integrating 1 from 0 to x. What's the integral of 1 from 0 to x? Integral of 1 from 0 to x. Well, if I integrate from 0 to x, this function, what am I getting? I'm getting the area under the graph. What does that look like? Well, this is constant height 1. And so I'm looking at a rectangle with base x and height 1. That has area x. So what does the graph capital F of x equal x look like? That's just a line with slope 1. And it goes up from 0 at x equal to 0 to 1 at x equal to 1. And then what happens after that? Do I get any more accumulation after that? Well, little f is 0 from there on, so I get no more. This is what capital F looks like. Okay? Now here's a typical thing that might be asked. What's the prob if 0 is less than a is less than b is less than 1? What is probability that a is less than capital X is less than or equal to b? Well, is this true? And if so, why? Do you remember this? If A and B are disjoint, probably the union of the two events is the sum of the probabilities. So think of this as being A. This is being the event B. What's this event in that case? This would be the event A union B. If x is less than or equal to b, it's either in here or here. It's either between these two numbers or it's less than or equal to that number. Okay? And those are disjoint events, right? You can't have x between here and less than or equal to that. So that's this thing where you just subtract this over there. Okay? And the first one is what? It's integral from minus infinity to b. What's the second one? It's integral from minus infinity to a. What if I subtract the second integral from the first one? I get the integral from a to b. Okay. This relation always holds. If you know that a random variable x has density function f, then the probability it lies between two numbers is the integral of the density between those two numbers. So far I didn't use anything about the particular density function we're looking at. This is just, I just use this relation here, which is a general relation between capital X and its density. Okay. So whenever you're asked to find the probability that a random variable is between, a continuous random variable is between two numbers, you integrate the density between those two numbers. Now let's use this particular example. Our numbers are like here and here. What would the integral of 1 be from a to b? Well, you're looking at the area of a rectangle of height 1 and base b minus a. So that integral is b minus a. This is called, again, the uniform random variable. It corresponds to picking a number at random between 0 and 1. If you hear the phrase pick a number at random between 0 and 1, it means take a random variable x with this density, that density there. Probably the most important random variable is the normal. So let me repeat here. This relation is a general one for a random variable x with a density f. The probability x is between these two is integral a to b of x dx. Okay. Okay, so here's a random variable that has a so-called normal distribution with mean, mu, and variance sigma squared. We'll see what those terms mean later. but they're just two parameters that describe this random variable. Its density is given by might look a little complicated now, but by the end of the 3 weeks, you'll be dreaming about this. If X has a normal mean 0 variance 1 distribution, then f of x is equal to 1 over square root 2 pi e to the minus x squared over 2. And this is minus infinity less than x less than infinity. So for this random variable, and in fact for any continuous random variable with density little f, the probability capital X is between minus infinity and infinity would be this, right? That's just taking a equal minus infinity, b equal plus infinity here. And what should this number be? What's the probability that the random variable is a number, is what it's saying? 1. So the integral of a density always has to be 1. So in particular, the integral of this density should be 1. And in fact, is that 1? Let's think for a moment what the graph of this looks like. What does e to the minus x squared look like? This is an even function. Goes to 0 at plus or minus infinity, and its value at plus x is the same as its value at minus x because you square x, right? X squared and minus x squared are the same. So it looks like that. So the integral over the interval from minus infinity to 0 would be equal to the integral over the interval from 0 to infinity. So this would be equal to square root 2 over pi integral 0 to infinity e to the minus x squared over 2 dx. Right? In other words, I double half of this, and I get the whole thing. Yeah. Okay, so we want to show this is 1. And one way to show a number is 1 is to show that when you square it, you get 1. That number can't be minus 1 because it's positive. So let's square it. If we square that number, we get 2 over pi integral 0 to infinity e to the minus x squared over 2 dx. We want to show that that's 1. Or that this squared is pi over 2. So let's look at that integral squared. See, the problem we have is you can't integrate that. There's no way to integrate this. Nobody's ever found one in 300 years. Maybe that's 300? How long have they been doing calculus? Maybe 200 years. But here's a trick that an English nobleman thought of. You square it. So I'll just write it as the integral times the integral, but in the second one, I'll use a different variable. It doesn't change the value if I use a different variable. And now this looks like a double integral. 0 to infinity, 0 to infinity, e to the minus x squared plus y squared over 2 dx dy. And you took 2e, I suppose. Anybody here take 2e? Okay, what did you do in 2e? When you were doing multiple integrals, sometimes you would change variables, right? What variable looks appropriate here? What's the function in the exponent? X squared plus y squared is r squared from polar coordinates. So let's change this to polar coordinates. So which part of two-dimensional spaces are we integrating over here? X goes from 0 to infinity, y goes from 0 to infinity. That's the first quadrant, right? And how can you describe the first quadrant in polar coordinates? Theta goes from 0 to pi over 2. R goes from 0 to infinity. And we get e to the minus r squared over 2. And then what do we put here for instead of dx dy? R dr d theta. Okay? We integrate from 0 to pi over 2 d theta, you get pi over 2. Then we have integral 0 to infinity r e to the minus r squared over 2 dr. And how can we do that integral? I think you do a substitution. U equal to r squared over 2. du would be r times dr. So this becomes pi over 2 integral. What are the limits? When r is 0, u is 0. And when r is infinity, u is infinity. R dr becomes du. And here we get e to the minus u. And this would be pi over 2 minus e to the minus u evaluated between 0 and infinity. What's the value of this function at infinity? 0. What's the value of this thing at 0? Minus 1, but we subtract. So it becomes plus 1. So this becomes pi over 2. And so answer here is, this is pi over 2. Multiply by 2 over pi, you get 1, so yes. It does integrate to 1. And one preview. If x is a binomial random variable with parameter n and a half, so it's like tossing a coin n times, and you're counting how many heads you get. In other words, when n is large, a binomial random variable with those parameters divided by root n is essentially a normal random variable. That's called the central limit theorem. So today you saw the two most important probability theorems in probability, central limit theorem, we didn't prove it, and the law of rare events. So this is one reason normal random variables are so prevalent, is because of this result here. And it's true for more than just this example. We'll do that later. Okay, that's it for today.